When we track the origin of the digital age, we default to the heavy machinery of the 1940s. We picture vast rooms dominated by monolithic cabinets, thick wire patch cords, and human operators physically routing data. We assume that modern digital logic required electricity to exist, relying on glass vacuum tubes to flip the earliest ones and zeros. But years before the first electrical computer was powered on, true digital computing was achieved purely through the physics of sliding metal. It shows that binary logic is a mathematical abstraction that can be applied to any physical system, whether that system uses moving electrons or sliding rods. In 1936 Berlin, a civil engineering student named Konrad Zuse began assembling an alternative in his parents' living room. He built his machine out of 30,000 hand-cut metal sheets, slotted plates, and a standard vacuum cleaner motor. It contained absolutely no transistors, relays, or wires. Despite the crude materials, this was a fully programmable 24-bit floating-point computer operating at a mechanical clock speed of 1 Hz. But that presents an immediate physics problem. How do you process complex logic algorithms using nothing but moving steel? To understand the Z1 architecture, we have to stop reading data as an electrical voltage and start reading physical displacement as binary code. Modern processors execute their commands using electrical square waves. The Z1 operated on a purely physical, two-phase mechanical clock. Looking at this top-down schematic, the entire architecture rests on a single fixed baseplate. Every calculation is defined by how other plates move across this stationary plane. Phase 1 of the clock is the input. A control plate makes a precise vertical movement. Phase 2 is the execution. A moving plate slides forward in a horizontal pulse. The output relies on physical contact. If the blue moving plate strikes a third green plate, that physical displacement equals a binary 1. To make these moving plates execute logic, Zuse introduced a switching pin into the intersection. To create a NOT gate, which inverts an input signal, an upward motion of the yellow control plate forces the red pin out of its standard track and into a new position. Because that pin shifted, the horizontal clock pulse now slides completely past the green plate without catching it. Zero physical movement registers as a binary 0. A specific sequence of sliding plates successfully inverted the data. It is a perfect physical logic gate. A functioning CPU cannot operate on inversion alone. It requires complex logical operations like AND, OR, and XOR to execute actual mathematics. This schematic outlines the mechanical AND gate. Because an AND operation requires 2 separate inputs to dictate one output, we start with 2 yellow control plates side by side. To bridge these distinct inputs, Zuse introduced an intermediate floating plate, locked into the assembly by 2 independent switching pins. If only one input moves, the geometry fails to catch the horizontal clock pulse. Only when both plates move vertically do the pins align perfectly, catching the pulse and driving the output plate forward. By layering floating plates and slotted pins, Zuse achieved Turing-complete logical operations strictly through geometry. Processing logical operations is only half the battle. A computer needs an addressable place to store the results. This block diagram shows the Z1's memory architecture. It stored values in a 24-bit floating-point format, strictly dividing the memory into a sign bit, a 7-bit exponent, and a 16-bit mantissa. Reading any stored bit required a vertical plate movement to mechanically select the data point, followed by a horizontal pulse to extract the actual value. Feeding data into this memory required physical media. Because standard paper punch tape was scarce, Zuse loaded the machine with discarded 35mm movie film. Mathematical instructions and numerical values were manually encoded by punching square geometric holes directly through the celluloid film strip. Distinct memory blocks, complex logic processing, and dedicated input-output, the exact hallmarks of modern computer architecture, were running in Berlin entirely on perforated film and sliding plates. Multiply those single sliding logic gates 30,000 times, and you get the fully assembled Z1, a 1-ton labyrinth of shifting metal plates. Every single floating plate, switching pin, and memory read operation was perfectly synchronized by the rotation of that single vacuum cleaner motor. But the machine's operational life was incredibly brief. In December 1943, Allied bombing campaigns swept across Berlin. An air raid completely destroyed the physical hardware of the Z1, obliterating all of Zuse's original construction blueprints in the resulting fire. The physical erasure of the Zuse architecture created a historical void. 2 years later, the massive electronic ENIAC powered on in America, allowing it to easily claim the title of the world's first computer in the public consciousness. Decades later, in the 1980s, Konrad Zuse committed to an ambitious project. He sat down and completely redesigned the 30,000-part machine entirely from memory. He finished the painstaking reconstruction in 1989, managing to expand its capacity to an upgraded 64-word memory block. This 1-ton reconstruction now resides in the German Museum of Technology, proof that Zuse's mechanical logic gates, though slow and prone to jamming, were a functional alternative to the electronic path taken by his contemporaries. We reflexively associate computation with silicon wafers and flowing electrical currents. But electricity is simply a transport mechanism. Computation is the execution of logic. The Z1 proved that this logic remains the same, regardless of the physical medium used to manifest it.